Hello. We will start our exploration of ordinary differential equations today. So, what are ordinary differential equations? That's a natural question. First of all, they are equations. Second, the unknown in such an equation is not a number, but a function. And third, in a differential equation, we expect to see derivatives of this function. Here is an example. It's an equation, definitely, and yx is a function, and that's the unknown in this picture. We can also see some derivatives of this unknown function here, so this definitely is a differential equation. And finally, the word ordinary refers to the fact that these are ordinary derivatives. The function has only one variable, so we are not using partial derivatives, but ordinary derivatives. This type of equation is somewhat different, because when you look at it on the left, you can see some expression, essentially. This is a function here which depends on x. And on the right, we also have a function which depends on x. There is no y here or here, but that's just another function of x. So when we add them with y's and derivatives, this is still a function which depends on x. So x is a working variable, and it's a dummy variable. We could replace x with t, and the meaning would still be the same. Now, in general, we could actually mix up these derivatives in a more complicated way if you want, but this is a special case. It's a fairly popular case where the highest derivative that we can see over here was actually isolated. This is not always possible in mathematics, but in applications this is actually fairly typical, and most people focus on this special case, which is what we did in our definition. So here is a definition of ordinary differential equation. We have the highest derivative isolated, and on the right there is some expression, and the shape of this expression is coded in this function f. And the function f as input has the working variable, and then the function y and all the lower derivatives. The highest derivative is very important because it in a way determines the behavior of solutions and other important parameters. So that's very important, this number 3 here, and we call it the order of the equation. This is an equation of order 3. Before we move on, little interpretation. We can, for instance, imagine that y stands for temperature. Typically, we investigate some quantity, and this quantity changes. Everything changes in nature. Now, the change may depend, for instance, on the location. X could be a location. That's a good name for a location. For instance, I'm interested in temperature, and as I'm walking here, it gets colder a little bit. And then I'm walking back, and it gets warmer again. So temperature depends on location. It would be also fairly natural to let the temperature change depending on time. And then I would put t here. In applications, we usually use suggestive letters. For instance, I'm standing here, and there used to be some temperature here when I came in. I don't know, 30 centigrades. It's really hot this summer. And as I'm standing here, I'm actually warming up this environment, so the temperature goes up. So typically in applications, which is the source of differential equations, they are very important in applications, you study situations, you freeze them, and you look at what influences you can see that influence this quantity. I have some quantity here, and I ask, what is the influence? And if I am able to write down the influence mathematically, then this influence is trying to do some change, which is what we see on the left. So that's a typical interpretation of a differential equation. Before we move on with theory and with those general considerations, let's try a very simple example. Here we go. Imagine that this is the ground, and there is some object hanging in the air over the ground, but obviously it's not going to be there for long, we know that. It's most likely going to fall. So let's put some mathematics into it. The vertical axis will be the elevation of the object above the ground. And for simplicity, we will allow only vertical movement of this object. And here on the horizontal axis, I put t for time. So this is actually the graph which captures the elevation of this object with respect to time. Okay, here is some differential equation. Let's say this one. What are the influences? You freeze the moment, which is something that is happening a lot in cartoons. Somebody's running, there is a gap or a chasm, and this person comes over this chasm and stops in the air and starts thinking. That's the freezing moment. This person starts thinking, wait, what are the influences? And probably the most prominent influence is the gravity. You noticed gravity before, I'm sure. So here is the gravity. For simplicity, let's ignore other influences like the air resistance. This is really the major one for us, for humans, as we walk here. What is it trying to do? The answer comes from physics. Gravity is trying to accelerate. So it's trying to change the acceleration of the elevation, which is the second derivative of the elevation. We have to be a little bit careful. The gravity pulls down, but the elevation points up, so we have to change the sign. And that's a differential equation. Now you can notice that there is no variable here, no t. This is typical. People are lazy, which is actually not such a bad habit, and what they do, they drop the variable from the function. They just leave it where it is really needed. So when people, mathematicians, write an equation like that, but applied people as well, they would write it in the following way. Y triple prime is y plus y prime over y prime plus x plus e to x. That would be the typical form of such an equation. And we can see it here in our very simple differential equation. This equation, in fact, captures a law of physics. This is the law of gravity. Homogeneous gravitational field, no other influences. This all can be captured in one very simple line. That's the strength of differential equations. They capture laws of physics and other natural laws. That's why they are crucial for many sciences and for engineering. Okay, how do we solve it? This is actually an almost trivial example. That's why I chose it for the start. Okay, I see the second derivative here. It depends on time, essentially, so I can integrate both sides. I integrate on the left, and I get just the derivative, and now I will put the variable there so that we are back on the field of analysis. That's how we write things in analysis, but just temporarily. And I integrate on the right, minus gt plus c. In calculus 1, they kept telling us, when you integrate, when you find antiderivative, you always have to put plus c there. And today we will finally see why it's crucial. Extremely important, plus c. Okay, let's try it again, because it looks like a good move. I integrate again, and I get yt. This is wonderful. What do I get on the right? Minus 1/2 g t squared plus ct plus another constant. Okay, let's say d. I got a function. That's wonderful. I have a differential equation where the unknown is a function, and I obtain the function. That looks very good. Does it make sense? Is it a solution? Good question. What is a solution? Well, we don't need any new theory or any new idea. We know it from elementary school that when you have an equation and you find something which you think is a solution, you can check. You just take this candidate and you put it into the equation. So I have a candidate and I put it into my equation. I should differentiate twice. When I do it, this disappears, 2t comes down, and then I differentiate again. After I substitute, I get this. I get minus g is equal to minus g. Now, notice that this depends on time, in fact, although I do not see it. But there is time hidden in this function, and the fact that it disappeared after differentiation, that's just because this equation is too simple. Okay? But in general, you can see here, if I take some candidate and I put it here, 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 it becomes a function on the left and a function on the right. Now, what does it mean, equality of functions? That's a good question. And the important thing is, we have to specify where we are looking. That's extremely important. Let's see, do I have room for a little note here? A little side note. I claim that the function x is the same as the function absolute value of x. Is it true? The answer is yes, on interval 0 infinity. And now it's true. So when I'm comparing two functions, I always have to specify where am I looking at them. That's one of the key notions in analysis or calculus, if you want. And here it works the same. I substituted my function into my equation. And after I did it, I got equality of two functions. And this equality is true everywhere, on the whole real line. So I can put here t belonging to real numbers. And now it is a proper solution. So every time we find a solution to a differential equation, we have to specify the region of validity. Now, why did I put real numbers here? It would be also true if I put t belonging to 1323. That would be still true, but it would be less information. So we always try to put the largest possible set over here. But in fact, not just any set, but I will get to it later. We always try to put an interval. 1323, that's an interval. Real numbers, that's an interval, set of all real numbers. So we always put the interval of validity when we write down the solutions to differential equations. So we actually solved our first differential equation, and we checked by substituting into it that we are really right, that this is a solution. And now let's talk about it. Well, first of all, I can notice that actually I have infinitely many solutions because there are parameters here. That's important. Notice that there are two parameters and the equation is of order 2. This is not an accident. For well-behaved differential equations, there is this deep correspondence between the order of the equation and the number of degrees or the degree of freedom. I have 2 degrees of freedom here. This has an important impact on applications because usually the differential equations that we face, they do not come from mathematics but from some applications. Okay, let's imagine why this is true. Well, this is a law of gravity, and the law of gravity doesn't force a single outcome. For instance, I have 2 pieces of chalk here, and when I let them go, I will get 2 different outcomes because they start at different elevations. Yeah, you can see that. So it is natural that when you have a law of physics, for instance, captured by differential equations, then there is actually infinite many possible outcomes. I could start here and then fall. That's how the elevation develops in time. Or I could start over here at a different time, at a different elevation. I could also take this, what is it? Probably a stone, and instead of just letting go, I could flip it up. And then the outcome would be like that. It goes up, then the gravity wins and pulls it down. This is quite possible. So there are really, really many different outcomes that our differential equation allows for. And our solution actually captures it, which is wonderful. So that's an important thing that we should keep in mind. When we are solving differential equations, we can expect infinitely many solutions. It makes perfect sense. Now, interesting question. Okay, we are usually studying a certain procedure or a certain process. And when we are studying a certain process, we expect just unique outcome. How do we get a unique outcome? The answer is from other information that we have at our disposal. This is a function with 2 parameters, and by the way, when we write solutions like that, we always assume that the parameters can be arbitrary real numbers. We don't have to specify it because it's understood. Everybody knows it. Now you know it too. Okay, if you want to specify a certain situation, you will need 2 pieces of data because we have 2 unknown parameters here in the solution. For instance, I can say, okay, at time t1, the elevation was here, I released it, and at time t2, it hit the ground. So it's 2 pieces of information which we can write down as a formula. Let's see. Y at time t1 is some elevation y1, and y at t2 is some elevation y2. Then we can use this data to actually determine which parameters C and D fit. This is not difficult. We just take this formula and substitute it here. I prefer to show it with a different set of conditions. You will see why in a second. But in this case, I should be also able to do that, and I determine a unique movement, a unique fall of this object. And for instance, it may turn out that we actually threw this object down when we were releasing it, like a basketball. So it went like that. That's a possible movement as well. By the way, these are called boundary conditions, but they are not all that popular in this theory. When we talk about ordinary differential equations, they are much more useful in a slightly different theory, which is called partial differential equations. And one of the reasons is that those boundary conditions may not give you a unique solution. For instance, it may happen that you have an equation, and we will see such an example later, and the set of solutions is just sine functions multiplied by some constant. So let's see that the set of your solutions looks like this. And let's say that you have two boundary conditions. One is here, one is here. You want your solution to be 0 at two specific places. Now, if things are set up well, for instance, if there is 0 here and pi here, then you can have infinitely many solutions of this form. And I don't even have two parameters, I have just one. And still, one parameter, two conditions, that's not enough to force one solution, because there are many solutions like that. I can put anything for C. So these boundary conditions, they are very natural, but they are tricky, and we cannot build a nice theory about them. So I'm not sort of saying that they are useless, they are very useful in some situations. But we are going to build a nice theory here, and for that nice theory, they are not really the best. So what is the best? Well, we are going to look at the following type of situation. Usually, when we study some process, we have a fairly good information what's happening at the time that we start it. So there's a specific time t0, let's say. Here is time t0. And we know the original elevation. So y at time t0 should be some elevation y0. And when we are releasing, we actually know how we release it. We know whether we impair some initial velocity to this object. Do we flip it up at a certain velocity, or do we fling it down, or perhaps we just release it like that? So we have this information in applications very often. Complete information about the starting situation. So this is the initial velocity. And again, we have here a formula which has two parameters, and now we have two starting conditions. This is called initial conditions because they initiate the procedure. And when things go really well, based on these initial conditions, we should now determine a unique movement because we know how it started, we know how we've released it. So there are many possible situations if we have just information about the starting elevation. That's quite obvious. But if we also specify the initial velocity, then there is just one outcome. And that's what we should find here. Well, usually the time is actually up to us to determine. When we start some experiment, we usually switch on the timer as well. So typically, the starting time would be 0, and this will make my life easier. Let's see. What happens if I have the following initial conditions? So I have the initial elevation, I have the initial velocity. Well, I substitute my general formula here for y. What do I get? Well, I get minus 1/2 g times 0 squared plus c times 0 plus d is equal to y0. That's the first equation. Let's have a look at the second one. I have to differentiate. I have to take the derivative of y. Well, okay. Y prime is well, I have it here actually. I don't have to differentiate. But typically when we solve a differential equation, we have the solution, some formula for it, and then we can differentiate afterwards. So here's the formula. Minus g times 0 plus c should be the initial velocity. So I just rewrite these equations, keeping in mind that I know the function y, and then I know the derivative as well. And that's a set of two equations with two unknowns, c and d. And it may happen that it's not possible to solve such a system. But in this case, we are able to do that. From the second equation, we see immediately that c is v0. And then we look at the first equation. This term is 0, this term is 0, d is y0. So what we get is a certain solution, and now it's just one specific solution which looks like this. Minus 1/2 g t square plus v naught t plus y naught, t belonging to real numbers. And actually that's a formula which I learned when I was in elementary school and I started with my physics. And they told us if you have an object which is moving in a homogeneous gravity field, then that's the formula for the elevation. And now we see where it came from a general differential equation and from some initial conditions which are taken at time 0, which makes life much easier. Which brings me to the second paragraph in our definition. What is a solution? A solution is some function, okay, which has all the derivatives which are needed. This is also natural, of course, otherwise we cannot substitute. And when we substitute this function, this candidate, into our equation, to the left-hand side, to the right-hand side, we get inequality on some interval I, for all x's from some interval I, which is exactly what is written here. Now notice that there is written open interval. Why open? Well, we want to differentiate this solution, this function y, because we need it in our differential equation. Now we know that if I have a function and I want to differentiate, I need an open set. In this case, an open interval. However, the word open is in brackets. Why? Because differential equations typically come from applications, and there it makes sense to try something slightly different. Let's have a look at it. Where does this data come from? Well, from some experiment. I started it. I take a stone and I release it. Now, does it really make sense to talk about negative times in that case, when I just release a stone and start my timer? And the answer is no. So there is another possibility how to write this solution. And it's this one. It's not exactly proper mathematically, but it makes perfect sense in applications. So people very often do that. Concerning differentiability at time 0, well, we do not really worry about it. You could say something about one-sided differentiability, but it's better just to talk about continuity. So when I write something like that, I mean that the function y is differentiable, but for t strictly larger than 0, and I want continuity at 0. But people in applications then usually do not worry about the mathematical angle as much. Okay, so there are two possible answers. One of them is mathematical, and one of them is practical, so to speak. Okay, that's the first slide. Now we understand what it means when we say a differential equation, which we typically write without this variable, this dummy variable here. We know what to expect when we see a solution. It's some function, it can have parameters in it, or it can be one specific solution which is given by additional data. That's fairly typical. Let's put some definitions and see whether we understand them. Okay, this is not actually a definition, rather it's a convention. When we are solving a differential equation, sometimes we get really lucky and we actually obtain a formula which captures all possible solutions. I didn't talk about it here, but yes, this formula captures all solutions. There is no other type of a solution. So that's very useful if you have something like that, because you have a complete description of the situation. This is the holy grail of differential equations. You get an equation, and from that you extract a formula which captures all the possible behaviors. And this is called a general solution. Very nice, we always try to go for a general solution. And when we find it, we say that we solved this equation analytically. Analytically means we get a formula for the solution. Now, why is this not a definition? Because there are some exceptions. There are exceptional cases when we want to extend this idea of a general solution a little bit farther, but there is no consistent theory about it. You don't find it in books. It's just, well, people use differential equations in applications. They use them in practice, and there are certain ways which are very practical, but they are not worth capturing mathematically. So this is not a definition, because there will be some exceptions. We will see them soon. If using some additional information, we get just one specific solution, then this is called a particular solution. So that's a terminology which is used a lot. Typical way to get a particular solution is exactly this. First, you get a general solution, and then using some extra data, you get a particular solution. Now, I didn't talk about it much, but this is an extremely well-behaved example. This is probably the simplest differential equation you can think of. Other differential equations are much tougher to solve, and sometimes you're lucky if you look at the solution, you work for 2 days, and you get one specific solution. So there are other ways to get a particular solution, not through this general one, but then your situation is much worse because you don't have a general overview of the situation. By the way, I don't know how to solve this one, and I don't think it can be solved analytically. There are no methods known to me, and I didn't find them in any book or anywhere that would actually handle this differential equation. So differential equations are really very, very tough. Anyway, the most popular way to get the particular solution is exactly this one. You specify what's happening at the start. Now, if you get lucky and your differential equation has order n, you get a solution which has n parameters, and then you expect that you will need n conditions to actually specify a certain process, a certain specific particular solution. So this has a name. It's called initial value problem, or sometimes people call it a Cauchy problem. So how does it look like? It has two parts. Part one is some ordinary differential equation of order n. And again, we have the special form where the highest derivative is isolated. That's how we like it. And you have initial conditions. You have a certain starting time. I'm talking about time because that's a good mental idea, good mental image to have when you are talking about the dummy variable x. But it could also be location, whatever. Okay, so you have the initial time x naught, and you know the value of the unknown function. Then you know the derivative, which is the velocity, if you want to see it that way, and so on. Now you need n conditions. If you need n conditions, then the last derivative should be n minus 1. It makes sense. Here we needed 2 conditions, and the last derivative is the first derivative, not the second. So it also works in general. So there are some prescribed values for the function and its derivatives, and there must be n of them, and this constitutes the so-called initial conditions. Now, in general, there is no guarantee that if somebody gives you a differential equation and initial conditions, then you can find a solution. Because in general, the field of differential equations is really very tough. So what we will do, we will look at nicer cases, at nicer types of differential equations, and then it actually usually works like that. You get initial value problem with initial conditions, and you find a solution. This is the perfect way to do things. And in fact, most differential equations coming from applications, they are nice enough to work like that. So that's a typical setup.